So when we talk about the state of matter, alright, gases, liquid, and crystalline solid are three primary states of matter or phases. So we have the gas, we have the liquid, and we have the solid. Okay, and these molecules, atoms or ions, are held in a close proximity. Okay, by what you call as intermolecular interatomic or ionic forces. Okay, so for a molecule to exist as aggregate in anything, in gases, liquid, or solid, intermolecular forces must exist. Okay, so these states are actually a continent, means the solid, liquid, and gases. So they have two common factors determining the position on the scale of the state. The first one is the intensity of the intermolecular forces. The second one will be temperature. Obviously, when we talk about the intensity of intermolecular forces, of course, the solid will have the highest, followed by the liquid, followed by gas. And as the temperature go higher, the solid will turns to liquid and melt as liquid and evaporated as gas. So when we talk about the states of matters, for example, solids, liquid, and gases, we need to understand the property of each. Okay, and in the gases, we can categorize the property according to densities, shape, volume, and strength of intermolecular forces. All right, so I guess you have learned about this in your secondary school, so I assume you know this by now. So before we start, I would like to make clear about what is the difference between atom, ions, and molecule. So beforehand, can you please tell me, hydrogen is an atom, ion, or molecules? It should be an atoms. Okay, when you have Na plus, Cl minus, those are ions. Okay, and says you have a water, all right, H2O, you have a lone pair, and this is a water molecule, and this is what you call a molecule. Is a combination of different atoms. And when you look at the bond, all right, the bond between the hydrogen and the oxygen atoms, this is what you call intramolecular forces, because it happened within the molecule. And says you have another water molecule, okay, and since this is electronegative, and they will have some kind of hydrogen bond with the molecule nearby, and what you call them is a intermolecular forces. Okay. So this is an explanation on intermolecular forces. So intermolecular forces are forces of attraction or repulsion between molecules. The forces between a pair of molecules depend on the distance between the molecule, and they are usually attracted to each other over a wide range of distance, but once they get very close to each other, they will start to repel. Okay, and it is very important in determining the state of matter as what I have just mentioned. So when we talk about intermolecular forces, the physical property, for example, first one, melting temperature, boiling point, boiling, L-I-N-G, boiling point, okay, vapor pressure, evaporations, viscosity, surface tension, as well as solubility, are all related to the strength of intermolecular forces. Alright, so the amount of the intermolecular forces is important in the interpretation of various property listed here. Alright, okay, so the intermolecular forces are much weaker than the intramolecular forces. Okay, for example, we have 16 kilojoules per mole for intermolecular forces, and we have 431 kilojoule per mole for intramolecular forces of acid hydrochloric. Right? So when a substance melt or boil, intermolecular forces are broken. Okay, and please take note, it's not the covalent bonds, okay, but the intermolecular forces. It is very different. Covalent, they bind, for example, I have H2O. Okay, we have here the chemical covalent bond, okay, and the intermolecular forces is between the molecule. Alright, okay, so when a substance condenses, the intermolecular forces are formed. So when they condense, means they are from the liquid, no, they are from the gas, for example, to liquid, right, liquid, so they condense. Alright, okay, in these conditions, intermolecular forces are formed. Right? There are different types of intermolecular forces. It is divided into 4. The first one, van der Waals forces. The second one, hydrogen's bond. The third one, ion dipole. And the fourth one, ion induce. Ion interact with induced dipole. Right? So in the van der Waals forces, is divided into dipole-dipole. And the second is dipole, induced dipole. Alright? And the third one will be between the molecule, induced dipole, interact with another induced dipole molecules, or what you call as London dispersion forces. Okay, so firstly, let's talk about the van der Waals forces. In general, van der Waals forces of attraction account for the molecular interaction involved in solubility, complexation, and numerous other physical bonding phenomena. Okay, they are actually weak forces compared to covalent bonds, which is generally around 50 to 100 kilocalorie per molecule. Okay, so there are different types of van der Waals forces, as we mentioned just now. The molecule which are polar, or actually called as a permanent dipole, having both a partial positively charged end and a partial negatively charged end. Let's say this is a molecule, alright, and they are polar, for example, and they have a partial positive here and a partial negative charge. Okay, and this is a permanent dipole if they are polar. Alright, and this molecule align themselves so that the negative pole of one point to the positive pole of another. So let's say you have a molecule in this way, say they are positive here, negative here, so they will align. Positive here, negative here, they will align. Positive here, negative here. Okay, and the energy of this attraction is around 1 to 7 kilocalorie per molecule. Okay, an example of a dipole force is hydrochloric acid. Okay, and what are the other forces involved in van der Waals? The second one will be dipole interacted, okay, with an induced dipole molecule, and this is also what we call Debye forces. Debye forces, alright. Okay, in this condition, we have the first molecule which is polar, okay, positive, negative, and we have a non-polar molecule, and which the non-polar molecule will be easily affected by the polar molecule, okay, and produce a what you call a temporary electric dipole in the non-polar molecule. Okay, and these forces of attraction are generally weaker than dipole. Alright, an example of this molecule will be ethyl acetate, methylene chloride, and also ether. Okay. So the third type of van der Waals forces is induced dipole forces. Okay, and how these forces happen? When you have two non-polar molecules that are close to each other, okay, two non-polar molecules, and nucleus of one molecule could actually attract, okay, electron, okay, of the other molecule, okay, and this cause the electron cloud distorted, alright, and form an instantaneous dipole molecule. Okay, so what is the key point for these forces? When you have two non-polar molecules that is close to each other and cause the distortion of the electron cloud. Since the induced dipole molecule is temporary, so both of these non-polar molecules will generate the forces that are weakest among the all, or you can call it as London dispersion forces, which is the weakest among the three of van der Waals forces. Which is the weakest among the three. Okay, next talk about hydrogen bond. The interaction between a molecule containing an hydrogen atom and a strongly electronegative atom such as fluoride, oxygen and nitrogen, and N is termed as hydrogen bond. This happens because the hydrogen atoms are small size and it has a large electrostatic field. Okay. Hence, it can move closely to an electronegative atom and form an electrostatic type of union. Okay, so hydrogen, they form electrostatic type of union with the electronegative atoms, which is also known as hydrogen bond. Okay, so the example of hydrogen bond is water molecule. The structure of an ice, okay, when the water is freeze, is an open and well-ordered three-dimensional arrangement of the tetrahedral with the oxygen at the center and the hydrogen atom at the four corners. So you have the ice structures, open. Okay, this is attributed by hydrogen bonds. And other example, hydrogen bond also responsible for DNA structure and also protein structure. So protein folding in a helix is a consequences of hydrogen bonds. Okay, and usually the hydrogen bond in proteins involve the hydrogen bond with oxygen and nitrogen atom. So oxygens and the nitrogen H atoms. Okay, and these hydrogen bonds of most important in maintaining protein structure are those between the peptide backbone, which is the NH group, okay, this one, and the backbone carbonyl groups, which is this one, and connected by hydrogen bond, and this maintain the peptide structure and also the DNA helix. And says so the hydrogen bond is very unique bond. If no hydrogen bond exists, so no protein, no cell, no animal, no human, no world. Okay.
Talking about H-bonds. These attractions do amazing things every day. You can find them in water and DNA. Maintaining these structures in amazing ways. Hey, talk about H-bonds. Without them, water would just boil away, and nothing would be alive today. They're so important that it's pretty cray. Hey, talking about
hydrogen bonds are strong dipole attractions. Important properties come from these cool interactions. Wait, a dipole-dipole interaction? What's that all about? We gotta know how that works before checking them out.
Dipole-dipole interactions occur between polar molecules with different electronegativities. This means one of their atoms has a higher tendency of attracting a larger electron density. So a polar molecule's partially positive side attracts to the other's partially negative side. This is basically a dipole-dipole interaction. H-bonds are a special type of these cool attractions.
Talking about
H-bonds. These attractions do amazing things every day. You can find them in water and DNA. Maintaining these structures in amazing ways. Hey, talk about H-bonds. Without them, water would just boil away, and nothing would be alive today. They're so important that it's pretty cray. Hey, talking about
H-bonds only occur between hydrogen and atoms of oxygen, fluorine, or nitrogen. The NO or F atoms need a lone electron pair, or it wouldn't be H-bonding and we wouldn't need a care. Why NO or F? Why not other atoms?
It's because of the high electronegativities of them. Since hydrogen has a low electronegativity, there's a huge difference in this value between H and these three. This creates the high strength within H-bonds. They're only weaker than some covalent and ionic bonds. This makes them stronger than other dipole interactions, making them pack quite a bit of attraction.
But why the lone pair? Why do you need that?
Because it causes other polar molecules to attract. The hydrogens of polar molecules actually get attracted to the lone pair like a strong magnet. These forces aren't just intermolecular, but can exist within molecules and be intramolecular. So the strong forces of H-bonds can form a number of strong interactions and chemical structures.
Talking
about H-bonds. These attractions do amazing things every day. You can find them in water and DNA. Maintaining these structures in amazing ways. Hey, talk about H-bonds. Without them, water would just boil away, and nothing would be alive today. They're so important that it's pretty cray. Hey, talking about
H-bonds are a vital phenomenon as a whole. These special interactions have a pretty big role. They form many important everyday structures, such as water, proteins, DNA, and others. Between H2O molecules, the two attached H's attract the O's on other molecules. It's quite basic, but these basic attractions are also quite key because they give water very special properties. Water is very cohesive due to these interactions, since H2O molecules stick together from the attractions. Water's strong adhesion is also very cool, since H-bonds can attract to other molecules. This explains why water can stick to glass instead of rolling up into a small ball or mass. But this isn't just the only important part, since H-bonds increase the point at which boiling starts. More energy is needed to break up H-bonds in water, thus increasing its boiling point and making it hotter. Without H-bonds, Earth's water would just boil away, making it impossible for any organisms to survive a day. Hydrogen bonds are also in DNA, maintaining a helix structure they have every day. The H-bonds in the base pairs keep it together and prevent many genetic mutations and errors. Without them, DNA would have a plasmid structure, allowing for genetic mutations to amount in great numbers.
This would cause more cancer, shorter lives, and other problems, but thank God for H-bonds because they're just so awesome. H-bonds aren't just making helixes in genes, they also do the same in our own proteins. Their secondary structures are what H-bonds form, which is necessary for all proteins to perform. So without H-bonds, these things would disappear and the formation of life would be nowhere near. Now you know how H-bonds are so vital. This chemical phenomenon is needed for survival. Talking about H-bonds. These attractions do amazing things every day. You can find them in water and DNA. Maintaining these structures in amazing ways. Hey, talk about H-bonds. Without them, water would just boil away, and nothing would be alive today. They're so important that it's pretty cray. Hey, talking about H-bonds.
Okay, now let's talk about the ion dipole forces, number 3. And let's say you have an ion, Na+, for example, and they will interact with a dipole molecule, okay, which is a polar molecule. For example, let's take the example of water, which is polar. You have a H and a O. Okay, so how do you interact with Na plus? So let's say you have an ion Na plus here. Okay, since this is a positive ion, and they will interact with a polar water molecule by having the negative oxygen on their surface, and they interact this way. Alright, this is how an ion dipole forces form. Okay, and says in another case when you have Cl minus, alright, and this is a negative molecule, and you will interact ion dipole this way, because the minus, they will attract the positive, and they attract ion dipole forces in this way. Alright, the hydrogens bound to the surface of the chloride ions, and you have the oxygen directed outwards from the chloride ions. Okay, then this what you form, the ion dipole forces. Alright, so by understanding these forces, so let's say if you have a crystal structure, alright, a crystal, okay, crystal, alright, or you can say, for example, you have a salt, the salt of silver nitrate, okay, and the silver and the nitrate force, alright, the force between silver and nitrate is much stronger than the force between silver water or nitrate water. If that's the case, then you will have what you call insoluble salt. Okay, and let's say if you have sodium chloride, alright, sodium chloride, which they have the bond between the sodium and the chloride weaker. This bond is weaker than Na plus to water, and Cl minus to water is weaker. So the structure of Na plus Cl minus, this structure will easily break. Alright, if they are easily broken, then they will form what you call soluble salt. Okay, so we have example of an insoluble salt of silver nitrate and soluble salt of sodium chloride. This is due to the forces between the ion dipole in comparison to the forces between the ion in the salt. So the last type of force is ion-induced dipole, which means an ion-induced dipole, they can cause an induced dipole in another non-polar molecule. Alright? Okay, by disturbing the arrangement of the electron cloud in the non-polar molecule, right? And this is simple. Okay, so let's look at some example of the effects of intermolecular forces to boiling point of hydrocarbon. So we have hydrocarbon of pentane, hexane, heptane, and so on. So from here onwards, you have the length, the what you call the length of the hydrocarbon longer. All right. So you have when you have the CH bond, you have the hydrocarbon longer, then you have more CH bond. So means you have more intermolecular forces. So for anything to happen, for example, the physical phenomena of boiling, you need to break the intermolecular forces. So when you have more intermolecular forces, then you need higher energy, right? In this case, you will increase the boiling point. So from carbon 5 to carbon 9, the boiling point increase accordingly from around 40 degree up to 150 degree. This is one of the examples. So let's look at another example with formaldehyde and ethane. So when you look at formaldehyde, they are slightly polar molecule. And when you look at ethane, it is a non-polar molecule. Alright, even though you have the higher CH bond in ethane, but because it is non-polar, the forces of non-polar molecule, alright, the intermolecular forces of non-polar molecule is much lower than the intermolecular forces of a polar molecule. So same thing you will expect with that. Formaldehyde will have higher boiling point and also higher melting point due to the higher strength of intermolecular forces. So again, now we have the example of a polar molecule with OH at the back, alright, and also a non-polar molecule, okay, but they might have the dipole induced because of the O, and the polar molecule, they can actually form what you call hydrogen bond, which is much stronger, okay, and when you talk about the polar molecule, the intermolecular forces is higher, so you expect the boiling point will be higher and the melting point higher. So as mentioned before, intermolecular forces can also affect viscosity of liquid, and obviously when you increase your temperature, and viscosity of the liquid will be decreasing. Okay, simply because when you increase your temperature, the kinetic movement of the molecule is higher, so the mobility is higher, the intermolecular forces between the molecule has been weakened. So when it has been weakened, the viscosity is decreasing. So this is the example of guideline that you can use to identify forces within a molecule if you know the structure of the molecule. For example, first you identify whether the molecule is polar. If yes, then you go through this. Then you ask yourself, do the molecule have an hydrogen atom bonded to F, O, or N? If yes, of course, then you will have the hydrogen bond. Okay. If no, then both London and dipole-dipole forces will exist. Alright. And if the molecule is non-polar, then you may only have the London dispersion force. Okay, because when you have the non-polar, they will just induce the dipole. Okay, and that's it. Simple. Same thing, this is another guideline which involve ion. So they have an extra portion of ion dipole forces and ionic bondings. Alright, so I expect if I give you a molecule, you will be able to tell me which force involved. Alright, so these are the reference that I use to prepare the slide, so you can go through them. Okay, and if you are interested, you can read Martin Physical Pharmacy, which most of the material come from here.